Hey folks, as promised, the fourth video on regression, working through an example. Okay, so what I did was I went into the data that you all gave to me at the beginning of the semester that asked for things like your favorite color, your gender, your height, your age. It also asked for the number of siblings that you have and the number of pets you currently own, as well as the number of pets you've owned forever in your life. I chose two columns randomly, number of siblings and number of pets. I then randomly organized these. I kept them together, so your number of siblings is still next to your number of pets. But then I randomized them all up so that they weren't in the same order they were before. And then I just grabbed the first 15. Okay, so I randomly selected 15 participants' data from our class. So these are 15. You might be able to see you. So if you're the person out there with 7 siblings, that's you down there at the bottom of that data right there. The rest, who knows? Okay, so what we're going to do is treat these two columns, and I only did the 15 instead of the entire class, so that we didn't have 30 numbers we had to go through on the screen, right? 15 is enough to demonstrate this example. All right, so let's go through it. Let's calculate our correlation coefficient first, then we'll talk about standardized slope and regression, and we'll do the whole 9 yards, okay? So this is our correlation coefficient equation. Right? Doing this allows us to calculate the Pearson correlation coefficient. So if you look at the equation, let's focus on the numerator and we'll get that done first. So PEMDAS, right, the order of operations, we start with the things in the parentheses. And so in the first set of parentheses is x minus the mean of x. In the next set, y minus the mean of y. So let's start there. Let's go ahead and set up a column with x, set up a column with y, and get the mean of each of these. Okay? So the mean of our x data, if we add all those up and divide by 15, is 2.53. The mean of our y data then is going to be 1. Nice and easy, right? So let's add those means in there in 2 separate columns. You don't have to do this if you don't want to add that extra column in there. I just like to have redundancy in my tables so that I guarantee I didn't leave anything out. Okay, so, sorry, my puppy is here demanding that he learns about statistics as well. Once we have the mean of each of these variables, we're just subtracting it off, right? You've done this several times now. You know how to do standard deviation, and this is just one of those steps in the standard deviation process, so it's easy to do. So we subtract off the mean from each of those raw scores, right? So x minus the mean of x, we get all of these values. Then y minus the mean of y, it gives us all of these values. Okay, so we're almost there. We have the contents of this parentheses and the contents of this parentheses, and now it says we have to multiply those two parentheses before we then, notice the sigma's all the way on the outside, before we then sum up all of those products. So we need a new column, right? We need a column that now has x minus the mean of x times y minus the mean of y. So I got rid of those columns that just had the means in them in order for this to fit a little bit better, but the means are still down there below, 2.53 and 1. So now what we want to do is work with just those two columns. Now look, I normally don't recommend using highlighters in your book, and that's not because it damages the book. It's because most research suggests that highlighting and underlining does nothing for memory. But it does help you keep track of things. It does help draw your attention to the right location. So I'm going to recommend that as you are doing these calculations, when you get to this step and you're about to multiply the x minus the mean of x times y minus the mean of y, get out your highlighter and highlight the column for x minus the mean of x. Then highlight the column for y minus the mean of y. They can be in the same color, different colors, it doesn't matter. That way you don't accidentally use a number from one of the other columns when you're multiplying. It's very easy when you're sort of passing back and forth across the table to do that. So use these tips, use these tricks to avoid those sorts of problems. Then, once you're good, multiply the negative 2.53 times the 0, negative 1.53 times the 0, and so on and so forth until you get this fully fleshed out column of products, right? The x minus the mean of x times y minus the mean of y. Easy. What's the next step according to that equation? We have to sum them together. So we add all of these numbers up, and amazingly, despite these tiny little decimal differences, it sums to an even 16. So this example is actually working out quite well in terms of easy numbers to work with. They won't always be quite this simple, right? Okay, so what's the next step? The denominator. Right? It says that we need to take the square root of sum of squares x and sum of squares y. So let's go ahead and put the 16 up there in the numerator and say, this is our last step, sum of squares x, sum of squares y. We're almost there already. Because if you look at those two highlighted columns, that is the step right before the sum of squares, right? The next thing you would do is simply square all those values in the green column and then add them together and get sum of squares x. square all the values in the purple column, add them together, you get sum of squares y. So let's add those tables in, right? And what you'll notice is that by the end, you've got a lot of columns in this table. So it's best when you design your table ahead of time, you leave plenty of space, right? Turn your paper sideways if necessary, use graph paper, use whatever's going to help you keep it organized, and then add all of these columns. X, mean of x minus the mean of x minus the mean of x squared, y minus the mean of y minus the mean of y squared, and x minus the mean of x times y minus the mean of y, right? All of those possibilities, that way they're already in your table, and you don't later on go, oh crap, I gotta add another one, and I didn't draw my lines far enough. So, but again, just think about that kind of thing ahead of time. All right. We have our columns now added in here. We just have to square those values, like I said. So we take the negative 2.53 and all of those, we square them up, right? So everything in the green column here gets squared to produce these values. Remember, pay attention to your calculator. My calculator is stupid. If I enter in negative 2.53 and I square it, it would tell me it was negative 6.4. But that's because my calculator treats the negative sign in that case as sort of being like a negative 1 times whatever that value is, as opposed to the negative being the value that gets squared. So just know your calculator, right? Squared values can never be negative because squaring takes away that negativity, right? All values are positive when they've been squared. That's in fact why we do this step. So do it for the green ones. Do it for the purple ones, do it for whatever color you happen to make them. Get those squared deviations for both, sum those together so that we now have a sum of squares for x, a sum of squares for y, right? In this case, it would be 47.72 for x and 12 for y. So we're going to throw those up there. Let's go ahead and put them into the equation. Now we have 47.72 times 12. Let's work that out before we worry about the square root. Right? That product is going to be 572.64. So again, we're just working through the calculator at this point. Take the square root of that value. You'll get a 23.93. And then finally, if we do 16 divided by 23.93, we find our correlation coefficient, 0.67. All right, we did it. Sweet. All right, that was not hard. Okay, we found a positive correlation coefficient, which makes some sense, perhaps. A number of siblings and a number of pets might be related, in that if you're the kind of family that has lots of family, has lots of kids, maybe you just love to have things running around the house. And so you've got cats and dogs and stuff like that. Or maybe with lots of siblings, you're more likely than to have siblings that have pets. Yeah, if I'm an only child, I might have a cat. But if I have 3 brothers that each have cats, then all of a sudden my family has 4 cats instead of just the one. So again, you know, why it's positively correlated, that's a completely different sort of discussion right now. It is positively correlated, and at least in these data, fairly strongly, it looks like, right? Above the 0.5 metric that Cohen uses for what he would consider strong correlations. Okay, so what else do we have to do here with this? Well, we should really think about getting beta weights and things like that, right? We should really think about coming up with all of the other values that we want and getting our regression equation solved. Okay, so I'm going to put some relevant numbers up here, right? 47.72, 12, those are our sum of squares. I'm going to keep the correlation coefficient up there. And note that if we need standard deviation, which we're about to, that's easy. We already have sum of squares x. Right? So if we want the sum of squares, if we want the standard deviation for x, we simply divide by the number of scores in x, right? And then take the square root. So that's simple. Let's go ahead and do that. Put the 47.72 in here. Put in 15, because that's how many individuals there are in that particular class or in that sample. So we're going to throw it in there as 3.18. We'll throw that over here. Now we can do it for y. 12 divided by 15 is going to give us a standard deviation of y of 0.89. So now we have standard deviation of x, standard deviation of y. We need that because we're going to use it when we calculate our regression equation. So let's do that. Now we need to calculate our regression equation. Remember, the equation is y equals a plus bx. We have to figure out what a and b are, right? That's our goal. A is y-intercept. We already discussed how y-intercept is the value of y when x is equal to 0. So the way that we figure this out then, what that predicted y value would be, is by first setting x to 0. So we think about coordinates as xy. That coordinate is now 0, comma, y hat, because we don't know what y hat is. We've already talked about the process for this. It uses the z-score formula, right? So the z-score formula we know. I put some subscripts in there to be very clear that we're using the mean and standard deviation of the x data, not of the y data here. So we add in a 0, We add in the mean and standard deviation of that x data, right? We have that off to the side there. We've already calculated in previous steps. So 0 minus 2.53 equals divided by 1.78. Simplifies then to negative 2.53 over 1.78, which gives us a z-value of negative 1.42. Okay, fairly straightforward, easy steps. We now have a z that represents how many standard deviations below the mean, 1.4. A score of 0 would be in there. Okay, now we need to get a predicted y-score, and we do so by taking a trip through the z-score of predicted y train station, if you will. It's a weird analogy. Anyway, we have 0 y hat. We know that the z of x for that 0 is negative 1.42, and we have this lovely equation that says that if we multiply our correlation coefficient by that z-score, that we will be able to get the z of that y-score we're looking for. Right? So we plug in 0.67, our correlation coefficient, with negative 1.42, the value that we calculated in the previous step, and we get a z for the predicted y of negative 0.95. Okay, easy. Now all we have to do is get that z-score back into a raw score, a y value, and we have the second part of our first coordinate. Okay, so in order to do that, we use this rewritten z-score formula. This is just the same formula as for z-score, it's just solving for y now instead of for z. So we are looking for y hat, that thing all the way on the left. We can plug in our z of y score that we just got on the previous slide. We already know the mean and the standard deviation of that y data, so we can plug all of that information in. We get 0.9 for negative 0.95, excuse me, times 0.89, the standard deviation of the y data. Notice we're using y data right now because we are trying to figure out y. Earlier we used the x because we were trying to find the z of the x data. Okay, so negative 0.95 times 0.89 plus 1. Okay, it's very simple. Do the math. Simplify it again, and you get y equal to 0.15. So our y-intercept is 0.15, right? So we can plug that in. We now have our first set of coordinates, 0, 0.15. Remember, in order to calculate slope, we need 2 points on the line, so we have to figure out a second point somewhere along that line. So we're going to do the same thing. We're going to calculate a z-score for x equals 1 this time. So we have all the same steps. We're just going to start with a coordinate of 1, y hat and solve our way through. So we still use the z-score formula. We plug in 1 this time. We're using the x data because we're finding the z of x. We find it to be negative 1.53 over 1.78, giving us a z-score then of negative 0.86. Next step, we need to plug that in and multiply it times our correlation coefficient, right? So we multiply that times the correlation coefficient of 0.67, and we get a z of y hat of negative 0.58, right? These are just the same steps we did before. We're just now doing it with a value of 1 to start out the process. Plug that into this final formula then to get back our y hat value from that z of y, right? Using these values, remember the y values, we get a negative 0.58 times 0.89 plus 1, which is a 0.49 plus 1, negative 0.49 plus 1, which gives us then a final answer of 0.48. Okay, so fairly easy process here, right? And so then the next step is simple. We've got 2 coordinates now. We've got our 0 and 0.15. We've got our 1 and 0.48. We can then plug those into our slope formula. Slope, B, is rise over run. So it's y2 minus y1, right? Notice I color coordinated that there to show you that the first y value in those coordinates, because x is 0, that's our y-intercept. So we already have that, right? That's easy. We can plug it in, leave it there in our equation. Now we need to plug in these x and y values into the slope formula and get b, right, our slope. So we can plug those in. The second of the y values minus the first of the y values, so 0.48 minus 0.15 gives you a 0.33. Then on the denominator, the second of our x values minus the second of our y, or excuse me, the first of our x values, so 1 minus 0, again, that's why we choose 1 for the second point, because it makes this math easy. So 0.33 divided by 1 gives you 0.33, so the slope is 0.33. So our regression line, we have now finished. We created our regression equation. It's y equals 0.15 plus 0.33x. The slope is 0.33. You'll notice that 0.33 is positive. We also have a positive correlation coefficient, so this is internal consistency, suggesting we did that correctly. We can now see how that formula would play out with real values, so I can put in an x of 1, solve through that, and lo and behold, I get my y hat value. So not surprising, of course, because that's the coordinate that we calculated earlier. But we can go ahead and put that dot right there on the map, so to speak. And then we can do it again for another arbitrary value. So I'm going to keep it small value so that it stays on my little coordinates that only go to about 7 by 7 here. So let's put in a value of 6. All right, so y hat equals 0.15 plus 0.33 times 6. What's the y when x is 6? Turns out it's 1.49. We then have the coordinates of 6 and 2.13. 2.13, shouldn't that say 1.49? Hold on, the answer should be 2.13, not 1.49. Apologies there, I'll fix that so you probably won't even see one. So 6 and 2.13, apologies. Those 2 points are on the line. We just solved for them, right? So we know that they're on the line. So now we can draw the line, because all you need is the 2 points. So grab your ruler, slap it down between the points, and draw your regression line. Now you can see what the value of y would be at any of these possible values of x, right? So we can say, well, how many siblings, or excuse me, how many pets would I be expected to have if I had 20 siblings? What if I had 0 siblings? What if I had 4 siblings? And you can just follow that place on the line and say, well, it looks like with 4, you would have somewhere between 1 and 2. We're a little closer to 2 pets, probably. So most of you with 4 siblings would have 2 pets, but some of you with 4 siblings might have 1 pet. Right? And so that's roughly what the regression line would be telling us. And we did all of that in fairly easy fashion. Little tedious, a lot of plugging into your calculator. Hand might get a little tired writing those things, but it doesn't take too long, and it's really easy to follow. Now, we're not done yet. Let's get that beta weight real quick. Let's figure out standardized slope. That's easy because we already know sum of squares x and sum of squares y, right? We already calculated that. So we can plug that into the equation, solve real quickly for beta weight, and find that the slope of that line would be 0.66. Remember, that's if the two scales are put on an even playing field. They're in standard deviation units. They're no longer in the number of siblings and number of pets scales that they are originally. So what else is left? We've pretty much covered almost everything, except, of course, this monster. Sum of squares total and sum of squares error in service of calculating coefficient of determination. So let's get it real quick. Let's calculate that just to show you how that process would work. So we need y minus the mean of y. So I put the x and y data up there. Let's put the mean of y in its own column just to help us track through the subtraction process. Y minus the mean of y then, so 1 minus 1 is 0, 1 minus 1 is 0, and so on and so forth. Now let's square all those values. Now let's get that sum of squares, and we find it to be 12 for these particular data. So our sum of squares total is 12. Now we need to figure out our sum of squares error, right? We do that by using the regression equation to predict the y hat value using the x data. Okay, so I plug x into that equation. Y hat equals 0.15 plus 0.33x, right? And so an x of 0 goes in there. It's 0.33 times 0 is 0, plus 0.15 gives us a predicted value of 0.15. Okay, so that's where that first one comes from. We do the same thing with each of those x values, plugging them into the equation, getting a predicted y and writing it down. Then we subtract those predicted y's from the actual y's, right, giving us this column of data. And then finally we square all of those values, sum them together for a 6.65 in this particular case, and we have found our sum of squares error. Okay, now all we have to do is plug them into the equation and solve for r squared. So 12 minus 6.65 divided by 12 would be 5.35 divided by 12, which would be a sum of squares, which would give us an r squared coefficient of determination of 0.45. All right, so let's throw that up there. But then remember, there's an easier way of doing this. R squared is just r times r, just like 5 squared is 5 times 5. So if r is 0.67, we can actually use that correlation coefficient by itself to find out r squared without going through that lengthy process. And guess what? If 0.67 is multiplied times 0.67, it rounds to 0.45. So all roads lead to Rome, right? They all sort of lead together here in this particular case. So we've figured it all out. We got our correlation coefficient in pretty short order. That was the bulk of the work, though. Then we can get our regression equation pretty simply once we have all of that. And then the rest of this is really easy, because don't go through that long process for r². I've shown you. It works both ways. Do it the easy way by just squaring it. And realistically, I mean, this is a pretty easy process. It uses all the numbers that we've been dealing with. We've known how to create standard deviation. Okay. Enough already. My cat says she needs a break. So you guys go practice it. You need to practice, because that will ensure that you don't make the sort of little errors that you might on the exam or the homework. That's when you don't want to make the errors. You want to make them when you're at home, right? When it's on complete nonsense, just practice. Okay? So go do it. Cheers.
Say you have a lecture hall worth of students taking a multiple choice exam, and instead of studying over the past few weeks, they all decide to answer every question randomly. If everyone played along, the scores would look like this. Most would score right around 50, while some, by pure chance, would score very high, or very low. If you let the lucky ones take the exam again using their random guessing shenanigans, they wouldn't all hit home runs again. Their scores would actually look like miniature versions of the entire class. While some would score high again, some would score low, but most would float back down around 50. Likewise, the same thing would happen with the students you wouldn't want to take to Vegas. They all wouldn't just bomb again. While some would score low again, some would score high, but most would rise up to right around 50. You might be thinking that no one would guess randomly on every question, and you're probably right. If students didn't choose randomly at all, then every student would be expected to score the same on the second round as they scored in the first round, and this weird side effect would just be dust in the wind. But if there's room for any chance whatsoever, this side effect tends to show up. It's commonly known as regression to the mean, and it was first documented by Sir Francis Galton in his 1886 paper. All the while, being busy founding psychometrics, devising methods for classifying fingerprints, creating the first weather map, pioneering the use of questionnaires, conceiving of a measure to quantify normal variation, also known as the standard deviation, and inventing regression. Safe to say, the dude was busy. He noticed this when looking at how tall kids were. He examined the heights of 930 kids and compared them to their parents' heights. He found that the kids were actually closer to the average height than their parents were. That is, tall parents actually tended to have kids who were closer to the average height, even though some did have tall kids. And that short parents also tended to have kids closer to the average height, even though some did have short kids. This flew right in the face of common perception and intuition. Heights aren't completely deterministic. Most realistic situations fall between the two extremes of 100% random and 0% random, sort of like a balancing act. Remember the exams and the students? You can think about them as a combination of skill and luck. The students who scored high in round 1 were probably either skilled and had no especially bad luck, or were unskilled but got extremely lucky. When round 2 comes, it's the luck that's being re-rolled like a die, not the skill. The unskilled probably won't catch another lucky break, while the skilled, although prepared, will have a second chance to have bad luck. This is the regression to the mean bit. Those who did well previously are unlikely to repeat their success, just like the tall parents, who are actually more likely to have average height kids than more tall kids. And it's a similar story for the students who scored low on round 1. They're likely to do better in the second round just by pure chance, just like the short parents, who are more likely to have average height kids than more short kids. The idea of more skill leaves less up to chance might seem really obvious, but it's seriously overlooked far too often. Suppose you are testing a new drug for a terrible disease. I can't think of any good recent examples in 2020, so you'll have to use your imagination. You take the worst of the worst in the population and test the drug with high hopes to find that, after the first treatment, their conditions have improved. Great news, right? Remember the students? If you can't rule out randomness completely, then part of being in the worst of the worst is due to bad luck, like students who did poor on round 1. They were either unskilled and just not lucky enough, or skilled and really unlucky. And the improvement could be just the right combination of skill and luck. In other words, patients would be expected to improve a certain amount just by random chance. But by how much? And how much is because of the drug, if any? This is where control groups come into play. Having a group from the same worst of the worst population who don't take the drug at all lets you see if the drug improves health more than random chance would by itself. Any change in the control group is regarded as change due to random chance, and the leftover change in the drug group is regarded as change due to the effect of the drug. So what's the big deal? This is exactly what led instructors to believe that negative feedback trumps positive feedback. Students who did poor and got negative feedback would tend to do a little better afterwards, while students who did well and got positive feedback would tend to do a little worse afterwards. Luckily, psychological trials with control groups have shown that this view is totally backwards, and that regression to the mean was likely the guilty culprit. But without a control group, it's easy to be fooled, since it's impossible to tell what caused what. A wise man once said, "If something varies normally between two far extremes, it usually swings back naturally to values in between." From sport to crime and illnesses, we see this common theme, an effect we call, statistically, regression to the mean. Evidence-based treatments that doctors should assign use tests that will be randomized, controlled, and double-blind. Stopping self-deception before test results are seen stops them from being fooled by regression to the mean. If you like this video or would like to hear about other topics, subscribe, hit the like button, leave a comment.